Welcome back to The Explainer. Today, we're taking a really fascinating journey into the life cycle of electrical energy. We're going to ditch the dense, boring textbook math for a bit and visually map out one of the absolute most foundational components in electronics, the capacitor.
Okay, let's dive into this. You know that electronics are essentially just systems moving energy around, right? Well, in that system, the capacitor basically acts like the ultimate electrical water tank. But the big question is, how exactly does it store up that charge, and how does it release it the moment the circuit actually demands it? To make sense of it all, here's our roadmap for today. First, we'll look at charging up, then the discharging process, understanding the time constant, storing the energy, and finally, putting all that theory into practice. All right, Section 1, charging up the capacitor. Think about connecting a completely empty water tank to a really high-pressure hose. At first, water just rushes right in, but eventually, the pressure inside starts pushing back. In our charging circuit, which has a resistor, a capacitor, and a voltage source, closing the switch causes a very similar effect. As charge accumulates on those capacitor plates, it creates a potential difference that actively opposes the applied voltage, and that is exactly why we see the voltage curve shoot steeply upwards before slowly, gradually leveling out.
Now, instead of getting totally lost in the differential calculus behind that curve, let's just look at this beautifully elegant final equation. Lowercase v equals uppercase V times 1 minus e to the power of negative t over RC. What's truly amazing here is what happens as time stretches out toward infinity. That exponential term, it just shrinks right down to zero. So that means our capacitor's voltage perfectly equals the supplied voltage. Boom, the tank is completely full.
But what's happening to the current while that voltage is busy rising? Well, it does the exact opposite. Because all that accumulated charge creates opposition, it essentially chokes off the flow of new electrons. So while the voltage climbs up to its absolute maximum, the charging current drops exponentially right down to zero. Once that capacitor is fully charged, literally no more current flows.
Which brings us to Section 2, the discharging process.
As they say, what goes up must come down. And this brilliantly illustrates that perfect symmetry in physics when the system essentially runs in reverse. With a closed loop through the resistor, our initially charged capacitor is now acting as the power source. Both the voltage and the current decay, dropping smoothly back toward zero. But check this out. Notice how the current graph actually starts in the negative? That negative sign just indicates that the current is flowing in the exact reverse direction as the capacitor drains its stored energy back through the circuit.
Moving on to Section 3, understanding the time constant.
So we know it charges and discharges, right? But how fast does all of this actually happen? Well, every capacitive circuit has a built-in speed limit. We call it the time constant, and we represent it with a capital T. The formula literally couldn't be simpler. T equals R times C. That's the circuit's total resistance in ohms, multiplied by the capacitor's capacitance in farads, which spits out a value in seconds. This single, simple number sets the whole pace for the voltage change. So obviously, a larger resistor or a larger capacitor means a longer time constant, and therefore a much slower fill-up or drain-out time.
But why do we even care about T? Well, because of this magic number right here, 63.2%, when exactly one time constant has passed. So when time literally equals R times C, the math of that exponential curve dictates that a charging capacitor will have reached exactly 63.2% of its final applied voltage. Now, what's really interesting about this slide is how we can anchor that 63.2% value directly onto the physical charging curve itself. Think about it. If the initial rate of voltage rise just stayed constant, moving in a perfectly straight diagonal line, it would hit the full supply voltage exactly at time t. But because that pushback we talked about slows it down, by the time we hit t on the x-axis, the curve has only made it to that 0.632 mark on the y-axis. It gives us this highly predictable benchmark for designing circuits that absolutely rely on precise timing. Next up, Section 4, storing the energy. Okay, so we've established the speed of the capacitor, but how much actual work is done to fill our electrical tank? If you integrate the instantaneous power of the capacitor over the time it takes to charge from zero up to full voltage, you get this stunningly simple equation. Total energy stored equals 1/2 CV squared, measured in joules. What this tells us is absolutely crucial. The total energy fundamentally relies on the size of the capacitor, sure, but it relies on the square of the voltage. So doubling the voltage doesn't just double your stored energy, it literally quadruples it.
Finally, Section 5, putting theory into practice.
Let's actually put those derived formulas to the test on a real-world circuit. Here we have a 40-volt source, an 8 kiloohm resistor, and a 4 microfarad capacitor. Notice the two-position switch sitting up at the top. When we throw that switch to position 1, it connects the power source and begins charging the capacitor. But when we throw it over to position 2, it entirely bypasses the source, creating a new discharge loop. Let's move to and see how this builds. To understand the behavior here, we first just need to find our time constant. Remember, R times C. That's 8,000 ohms times 4 microfarads, which gives us 32 milliseconds. Now, if we throw the switch to position 1 for 10 milliseconds, we literally just plug that time into our charging formula to see exactly how full the tank gets. Flick it over to position 2 for 5 milliseconds, plug that into the discharging formula, and we can see exactly how fast those electrons flow backward. It's really just a matter of identifying the phase you're in and applying the right formula.
So let's do a really quick recap of the whole life cycle we've covered today. During charging, voltage rises against the applied source while current falls to zero. During discharging, both voltage and current decay, with the current flowing in reverse. The speed of this whole intricate dance is perfectly governed by the time constant, T equals RC, where it reliably hits that 63.2% benchmark. And lastly, the total energy stored inside this component is 1/2 CV squared. Look, understanding this foundational physics matters immensely, because these exact principles dictate the behavior of everything from the flash on your digital camera to the touchscreen on your phone. Before we wrap up, I want to leave you with a bit of a provocative thought to chew on. We know from our time constant formula that to make a capacitor charge instantly, we would somehow need to push resistance or capacitance infinitely close to zero. So if you tried to engineer a circuit to charge a battery instantaneously, applying this math to a real everyday scenario, what physical limits of real-world materials would you hit first? Like, could the physical wires even handle that infinite spike in current? Think about that, and let that curiosity guide your next steps into the physics of materials. Thanks so much for joining me for this explainer, and as always, keep learning.